The SUNY College of Environmental Science and Forestry, founded in 1911, is now the only institution of higher learning in the United States dedicated solely to the study of natural resources and the environment.
Improve Your World comes to you today from Walters Hall on the ESF campus in Syracuse. This is the home of the Faculty of Paper Science and Engineering. Here, we're in the middle of where classroom theory is turned into practical application. Hello and welcome to Improve Your World with SUNY-ESF. I'm your host, Don Torrance. Today we'll be talking with Dr. Gary Scott. Dr. Scott is the Associate Chair of the Faculty of Paper Science and Engineering here at ESF. We'll talk about teaching bioproducts engineering here at the school. In other words, how students are learning to create fuel from wood. But first, our first guest today is Dr. Tom Amadan. Dr. Amadan, very pleased to have you with us here today. Dr. Amadan is the chair of the Faculty of Paper Science and Engineering, and you're also the director of the Empire State Paper Institute, I understand.
Yep. Don, thank you very much for coming.
Well, it's a pleasure to have you here, and this is a very exciting operation we've got to discuss today because nothing is more of a headline kind of opportunity than discussing alternative energy, especially here based in New York State and at ESF and the research that you're all doing here. You've been developing a process to remove energy-rich sugars from wood. Can you tell us a little bit about the status of that? Because I know it's been under development for quite some time. You're waiting to get it to commercial application. Where are we in that process?
We're at what we call pilot scale, engineering scale. That's where we're doing it on the many cubic foot basis, creating 55-gallon drums of material that we then do some more work on. So that's a significant scale, well off the bench. You need some equipment like that around here to do it, but that's not full-scale commercial yet. That's where we intend to go within about 2 years.
In 2 years, you think this will be viable?
We feel a need for speed.
Right. Now, speaking of speed, we're getting a lot of motivation and impetus and perhaps money, too, from the federal government, from private industry. There's been a lot of talk about this billion-ton biomass for energy and other products. How does what you're doing here integrate with those efforts?
The billion-ton puts together the agricultural residue available for processing and the wood materials available for processing. We focus on wood. That's what we're good at. What our process does will work on agricultural residue, we believe, and we will get into it, but wood is our leading player. It's that half of that picture that we can help to fill in.
Now what you're doing too may turn the paper and pulp industry around, I understand, because it will help them towards new streams of revenue, new profitability, sustainability, perhaps even new jobs for people in this region?
We see increased jobs. When we look at the incremental revenue from this idea applied to the paper industry, and it's early on, remember, these are estimates, but it takes them from below the cost of capital to above the cost of capital. Sorry for the little bit technical words, but if you're below the cost of capital, you can't keep your physical plant up. Right. And if you're above it, you can keep going indefinitely. So that's an important incremental revenue addition for the industry. That motivates a lot of people out in industry as well as us.
So describe to us how this would work then. What the benefits would be, for instance, to a pulp and paper manufacturer if we were to, you were to help them along developing other uses of some of the byproducts of their processes.
The main real interest point to pulp and paper company is currently these energy-rich sugars that you mentioned are not used well in the process. 2/3 of them are lost. At best, they're turned into energy, but not good energy. They're not good at that. Take them out, turn them into ethanol, which is very good energy. It's portable fuel energy that's hard to come by. And their process actually gets more efficient. In other words, they're looking at their current way of manufacturing getting better and an incremental product that society wants badly and will pay them well to do. That's win both ways.
Right. We've heard an awful lot about ethanol lately. Most of what I think the American public hears about is food crop-based ethanol extraction from corn or sugar, crops like that. Why wood? What are the advantages of wood and what perhaps are the disadvantages?
The biggest advantage is lower cost, especially less energy invested. Trees don't require much fertilizer, they don't require much tending, so the amount of energy you had to invest to get them to catch the sunlight was very small. So when you recover a fuel from them, if you divide the energy you got by the energy you spent, you get a very good number, very positive number. I'm pleased with what we do with corn to ethanol. We get a positive number, but nowhere near as good as wood. So of course, not surprisingly, I like wood better.
Right. Now you're talking about wood as a crop, really, where I wouldn't want to leave people with a misconception perhaps that we're tearing down the remaining forests that we have in the United States in order to meet our energy gluttony, as some people have put it. Describe where your wood biomass is coming from, if you could.
Commercial forests only happen on land that is held meant to grow commercial crops and to grow them again and again. Doesn't get into land that is too steep or being held because of unique diversity. That land doesn't get touched. I don't see this having any effect on that. But the main thing we haven't mentioned is this will start a new crop for farmers, and it's already happening in New York. It's called biomass willow, shrub willows, where they're catching energy and put it into wood, small pieces of wood. But those small pieces, they work just fine in this process. And NYSERDA has funded the work to let us be able to show that, hey, they work really well. And private companies have begun to put out contracts to farmers in New York to grow willow. Now that is really, I think, getting smart about this energy situation.
Now we have talked about willow in the past on the program here, but you're concentrating too on hardwoods. What is the difference? What advantages do hardwoods have over a rapidly growing smaller plant like a shrub willow?
Well, now shrub willow is a hardwood. So
Good.
They work just fine. Rapidly growing small plants like loblolly pine in the southeast, or corn or soybeans. Then it comes to the chemistry of hardwoods is we built this process to be good at them. They are advantaged. We get more valuable products from hardwoods. And remember, willow's a hardwood,
right, I will remember that.
Than we get from any other species because the chemistry is right for this process.
Okay. So this is in conjunction with what others are doing with shrub willow. What kinds of trees are you investigating?
The tree we look at most is sugar maple. Most common tree in New York State. We started at, it's our model species. It also grows very well without humans having to put a lot of effort into it. It's out there in the woods, reproducing just like it always has since before we were here. So it's the model species. We have worked with mixed northern hardwoods, birch, beech, the three different maples actually in New York State, and then oaks and hickories, but really birch, beech, maple. That's what New York State is best at.
And do these trees have to grow large in order for that equation of energy put in to grow versus energy output at the other end?
No, and that comes to, I didn't give you as full an answer as I should have to an earlier question. When you harvest hardwoods and take them to make lumber, and make strand board and flake board and fiber board, and then what you think is what's left you take for paper, you look at the stand out there, 50% of the mass of what was taken away is still out there. It's stuff that was too crooked or too small to be used by any of those. This process wants that. In other words, it was already harvested, it was going back to CO2 because it was going to decay.
Right.
Instead of having it decay and get no value from it, we will bring it in and get energy for us to use, and then it'll go back to CO2, and then the trees will catch it again.
Higher levels of efficiency of use then?
Yes.
Okay.
Less waste left in the woods.
Right. We're going to see a little bit about the specifics of the process, but we're going to take a little break first and come back. Coming up next, Improve Your World's Dave White. He explores one of the key parts to making ethanol from wood. He talks with ESF student Christopher Wood about how to separate sugar from wood. You're watching Improve Your World with SUNY-ESF.
You can improve your world by what you plant in your yard. It is commonly believed that invasive species arrived in the U.S. accidentally. Not so, according to a study by the Brooklyn Botanic Garden. They found that half of the worst invasive plant species were brought here intentionally for horticultural use. Gardening with native species is an effective way to deal with this problem. ESF's Improve Your World website has helped to find the right trees and plants.
High fuel costs, diminishing oil supplies, global warming. The time is now for safe alternative solutions. SUNY College of Environmental Science and Forestry is working on renewable energy solutions. For example, SUNY-ESF is part of a team working to develop the commercial use of willow crops and other woody biomass in the Northeast for safe, clean bioenergy and bioproducts. We really can improve your world. You can be part of the solution. Go to esf.edu to find out more.
You can improve your world by learning more about it. From black bears in the Adirondacks to the restoration of Atlantic salmon in Lake Ontario and its tributaries, and the growing number of coyotes all across the state, SUNY-ESF offers details in its Environmental Information Series. Do we need to encourage growth or curtail it? Get the facts, then you decide. There's also advice for developing environmentally sensitive landscapes, how to test your soil pH, and what it means.
Welcome back to Improve Your World. We've been talking with Dr. Tom Amadan about extracting ethanol from wood. Now we're going to take a look at an ESF student who's been working with Dr. Amadan on one of the essential components of that process. Dave White went out and filed this report for us. Seems almost prophetic that the student, Christopher Wood, would end up working with this process.
Making ethanol from wood starts with big chunks of wood being turned into chips. Chips just the right size. The chips are poured into a digester. Water is added and the chips are pressure cooked to produce this brown liquid. Next step, find a way to extract the good stuff from the brown liquid. That's where ESF Junior, Christopher Wood, came into the picture. And what he helped develop was this nanofiltration system.
This is a membrane that's actually been taken apart. How this works is you actually have a membrane surface. This one's seen quite a bit of use, which is this material. And you force water, acetic acid, methanol, and furfural through that membrane.
Here's the small pilot system. The membrane is inside the long cylinder. The brown liquid is pumped up through the cylinder, and the concentrated liquid is returned to the tank where it can run through again and again until it reaches the needed concentration.
But it allows you a very clean separation. You don't have to add anything. You don't take a chance of changing anything by adding heat. You don't have to put in the energy of heating up all that water.
Here's what the liquid looks like at the start of the process. After nanofiltration,
this is the concentrated sugar solution. This is about 3 times more concentrated than what's in the bucket.
Next step, test the nanofiltration system at higher pressure, going from 100 to 150 psi, pounds per square inch, to 500 psi. Kind of like going from erector set to real life. The extract from the digester goes through a first screening and into this 500-gallon storage tank. Then through another screen and into a second 500-gallon tank. Then the larger scale nanofiltration system begins utilizing 4 cylinders as opposed to 1. Just like in the small pilot system, when the larger amount of extract reaches the right concentration, it goes into this 400-liter fermenter where the ethanol is produced.
So clearly, Dr. Amadan, there are other products that come out of this process that can be turned into commodities for profit. It's not only the ethanol.
Ethanol wasn't even the reason we got into it. We got into it for a biodegradable plastic, which you can also ferment these sugars into, and there's a faculty member at this college who's researching it. Once we got into it, we found acetic acid was going to be a very valuable co-product also. The sugars and the acetic acid are what nature gives us from the trees. Turns out acetic acid are worth 3 or 4 times as much as the sugars, but you don't get near as much of them. Now, if you're okay with it, I want to show you.
Walk us through the process here.
Let me walk you through the process, and then we'll interrupt it a few times to show some specifics. It really starts 20 miles south here in Tully, New York, at the Heiberg Forest, where we harvest the trees. Okay. That's the college owns that. Most of the time we work with maple. These particular logs happen to be red oak, which are also common in the southern tier of New York State. We start with the trees, we peel the bark off them. Actually, our graduate students do that. In commerce, they have a different way, which is a lot less expensive, but our students appreciate the extra money. And then we chip them, and that's this large circular item you see in the back here, heavy metal, and it will reduce these logs to things that, these are just wood chips. It'll take about 2.5 seconds for one of those logs.
Really? For one of these large logs.
Those to this. Now it can begin to be treated as if it is a chemical raw material. Okay. It's uniform enough. From these, we go into water. There's a few secrets. The Research Foundation has some intellectual property here that we worked hard to get.
That proprietary information.
Right, but we do it now at a scale of about over 50 cubic foot in diameter in the volume, meaning we'll get 4 or 5 barrels of water with sugar and acetic acid in it. Looks like this, brown color. Don, if you're willing to smell it.
I thought you were going to ask me if I was willing to take a sip.
I don't encourage that.
Although it doesn't,
we haven't
it
tested.
Smells quite
It
nice.
smells a little like a vanilla cookie
Yes.
with a little bit of acetic acid. You know, just
Yeah,
that little bit of vinegar,
soury to it.
and that's what it is. But this isn't ready yet. In fact, if you tried to ferment it, it wouldn't, for the same reason that pickles and sauerkraut stopped fermenting. There's enough acetic acid in here that it's pickled sugars.
Right.
Then we go into a separation process. Christopher Wood showed that
Right.
in the work that you looked at there. Using membranes, we squeeze water and acetic acid through. The sugar doesn't go through. Sugar gets more concentrated. We want it to be more concentrated because if you're going to make ethanol, you want it to be fairly high concentration of sugars to give you a pretty high concentration of ethanol. Then the acetic acid is ready to sell. We get some other products, a little methanol and some lignin and stuff that is going to pay for itself. But the big
Useful.
money makers, yeah, they go into commerce. There are people who already want them, want to buy them. They want to take the methanol and use that to make biodiesel, whole different process, but you need methanol or ethanol to do it. So we're going to get something, you know, it's kind of like the everything but the oink when the pig goes into the...
Right.
Okay, we're going to get something from everything. We're going to net produce water. It's not a water consumer. Water comes in with the wood, we clean it up, and we're going to use that other places in the process. And we're going to make the ethanol, which is what society, I think, is most familiar with.
Right.
Some of the other products, I mentioned the biodegradable plastic. Before it's done, I think society is going to be more excited about that one because it isn't made from oil. If it gets loose in the world, it will degrade. It won't, you know, hang around the necks of the birds and things like
Yes,
that. But we don't have time today to go to all of that. So we start with chunks of trees, turn them into small things, extract them. That big digester over there, I think you've also got some footage on that.
Right.
You've got footage of us chipping and screening. You'll
Right.
see it's a pretty straightforward process that looks a lot like the current pulp and paper industry, just different products.
So how close, for instance, to a commercial application is the extraction of acetic acid into the biodegradable plastics? Are we years away from that also, or is it closer?
3 years ago, I would have said we're going to make those plastics before we made ethanol. And you know what? Maybe we will, because they're worth about $1.20 a pound, whereas ethanol, depending who you talk to, is 20, 30 cents a pound.
Right.
So maybe we will make them. That's in that 2 year, 3 year from now, which is pretty fast in my standards in industrial development.
Right. But these are on parallel tracks. One isn't diverting resources
No.
or ability from the other.
They bring more resources because some people are interested in one and not the other. And each one, when we make an advance, helps us on the other one.
Right.
Science is like that. You know, you learn things,
More and
you
more.
apply them.
Absolutely. Well, it's wonderful the way all of these are integrated and coming together, and you've involved students at all levels of study in the research here, and hopefully in the application too. Dr. Tom Amadan, thank you very much for joining us. We really appreciate it today.
Thank you for coming, Don.
Okay, coming up next, we'll be talking with Dr. Gary Scott about how to get youth more interested and to get them educated about the kinds of processes we've just been discussing. Improve Your World with SUNY-ESF. We'll be right back.
You can improve your world by what you plant in your yard. It is commonly believed that invasive species arrived in the U.S. accidentally. Not so, according to a study by the Brooklyn Botanic Garden. They found that half of the worst invasive plant species were brought here intentionally for horticultural use. Gardening with native species is an effective way to deal with this problem. ESF's Improve Your World website has helped to find the right trees and plants.
High fuel costs, diminishing oil supplies, global warming. The time is now for safe alternative solutions. SUNY College of Environmental Science and Forestry is working on renewable energy solutions. For example, SUNY-ESF is part of a team working to develop the commercial use of willow crops and other woody biomass in the Northeast for safe, clean bioenergy and bioproducts. We really can improve your world. You can be part of the solution. Go to esf.edu to find out more.
You can improve your world by learning more about it. From black bears in the Adirondacks to the restoration of Atlantic salmon in Lake Ontario and its tributaries, and the growing number of coyotes all across the state, SUNY-ESF offers details in its Environmental Information Series. Do we need to encourage growth or curtail it? Get the facts, then you decide. There's also advice for developing environmentally sensitive landscapes, how to test your soil pH, and what it means.
And welcome back to Improve Your World. My guest now is Dr. Gary Scott. Dr. Scott is the Associate Chair of the Department of Paper Sciences and Engineering. Dr. Scott, welcome.
Welcome.
Thanks
you, Don.
for being here with us. We're going to talk a lot about this exciting new venture that the school's involved in, and also the opportunities it can open up for students who come to the program here. First of all, tell us a little bit about your new program here in Bioprocess Engineering, what the term means, and what the field is.
Well, we're starting this program in Bioprocess Engineering at both the bachelor's, master's, and PhD level. And it's growing out of the research that's been going on here for the last couple of years. And the way I like to describe bioprocess engineering, at least the way we're using the term, is that it's chemical engineering, but without the petroleum. And if you think about it, most chemical engineering programs are historically developed in terms of petroleum engineering, taking what we can do with oil, natural gas, and petroleum products and producing other products in it. What we're looking at this program to do at all levels is to what products can we get out of our natural resources in our renewable and sustainable resources. So things like the wood to ethanol, biodiesel are some of the examples of the technologies that would be involved in a program like this.
Now, is this safe to describe these as a growth industry?
This is definitely a growth industry. We definitely need to do something to get ourselves away from petroleum. And we see this as a way of developing the engineers and the scientists that are needed to help us develop this technology and get it into basically the mainstream so that we can pull ourselves away a bit from our dependence on oil.
And this is an undergraduate as well as a graduate program.
Right, it's both an undergraduate and a graduate. The undergraduate program is an engineering program that has a biology and resource focus. And it will involve quite a bit of chemistry. It will involve biology, it will involve math, but it will train the engineers to think about what products we can get from our natural resources. This includes even to the extent of pharmaceutical products.
I would assume then that the job market for students who would graduate from this program would be quite strong.
We think so. Being that there's a 4-year lag in producing graduates from a program, we have to actually be thinking about 4 years ahead, and we think the market 4 years from now will be there. We've had some of our cooperator companies that come in and do work with us saying that they're ready for some graduates now, and we just expect the demand to grow.
Now, if you could describe in some specific detail what the bioproducts industry is all about, I assume that it covers quite a wide range of things.
It can cover quite a wide range, and there are a number of programs that focus on different aspects of it. A lot of bioengineering programs focus on the medical aspects of it. Bioengineering, biomechanical engineering for prosthetics and other medical uses. We're looking more at the commodity, the resource aspect of what can we do to displace products away from oil. So some of the examples are the wood to ethanol, getting fuel from a sustainable resource such as wood. Another one would be the biodiesel, again using a sustainable resource that can be in the terms of soybeans and other products, and getting that into more of a sustainable resource type product.
Now, there's been a lot of government support, I understand, as well as private industry support for these kinds of research endeavors. Does that have an impact on what student support there would be for those who want to get into a program like this? We're
working on getting student support. We have an advantage in the Faculty of Paper Science and Engineering, as we've had a long-standing cooperation with industrial partners through a research organization called the Empire State Paper Research Institute, and also the Syracuse Pulp and Paper Foundation. And the Syracuse Pulp and Paper Foundation has been supporting students with scholarships to study paper science and paper engineering, which are our other programs which we've been delivering since about 1920. But they are interested in also developing scholarships for bioprocess engineering students. So they are going out and looking for money, and we're trying to build an endowment to offer student scholarships to help them study, to help them get into this field. And within, I think it was just last month, we had announced our first $10,000 donation to a scholarship fund to support bioprocess engineering. So we were able to offer a student this year a $500 scholarship.
Typically, what kinds of courses will a student study at the undergraduate level, and then we'll talk a little bit about the graduate level? And is there a research component for undergrads?
At the undergraduate level, the three main components of the curriculum are math and chemistry, because the basics, and that's basically engineering. And of course, there's a strong biological component. Right. So the students will be taking a fair amount of chemistry, but then also taking this and focusing it on the biological aspects. And then plus we're offering about 8 new courses to cover the undergraduate program in things such as bioseparation, systems engineering, and biological systems. And one of the important parts of our program is an internship program. We will be requiring all students to do at least one summer internship. And again, this is stemming out from our experience with the paper engineering program, where we have been requiring internships for many years and have a very successful program in internships.
Now, between the undergraduate experience and the master's or PhD experience, you have a certificate program. Could you describe that to us?
Right. Our certificate program is an opportunity for retraining of engineers in this area. It's a 15-credit, so 5-course graduate certificate. So they take, over the course of a year, 5 graduate courses.
Oh, it is a year-long program?
It is a year-long program. It starts in June and runs, it starts in August and runs through June. So, they take the courses in lockstep, so one follows the other directly. And it's 15 credits. It can be a stepping stone to a master's or a PhD, but they are awarded a certificate through the SUNY-ESF, so it is an official certificate. And this allows engineers and scientists that already have a BS degree to get a more concentrated training in this area. And this developed through a need seen by Bristol-Myers Squibb to train some of their personnel in this area. And so far it's been a very successful program. The first year we've had it, there were 15 students in the program, and this year there are 19 students in the program. And each year we've had to turn students away because of capacity limits.
So it's for young mid-career professionals.
Yes.
And obviously they need the support of their employers to come for an entire year, or do they study oftentimes at night or online, or are you making innovations like that?
This program has been designed to help the professional that's working. So they are offered all as evening classes once or twice a week. And it's essentially been designed around the schedule of a working professional. Yeah. And Bristol-Myers Squibb has been our primary source of people coming, and they do support them by supporting them and paying their tuition for the program.
Now, on the graduate level, master's students, tell us a little bit about their course of study and what opportunities await them when they graduate from the program.
The master's and PhD program, those are both research-heavy programs, so most of our students, or all of the students, are working on a research project with this area, with the coursework to give them the background to do their research. For example, one of the projects is getting the hemicelluloses out of the wood chips for the fermentation. And this one student is designing and modeling that process so that we can optimize it and getting the hemicelluloses, the sugars, out in the most efficient process.
So innovation is a big part of whatever research work they're doing here then?
Yes, the innovation and the development of these new technologies. And we are now working, and some of the students are working on this, is taking this process and working on the scale up. And so we take it from the laboratory scale to the larger scales.
Terrific. Where do you recruit for your students? Who are you looking for in terms of undergrads coming out of programs?
What we're looking for the graduate program is students that have a background in engineering, particularly possibly chemical engineering, or a background in paper science and engineering. We see this as not a strong divergence from the paper engineering program. We see this as a complement as a way for the paper industry to expand its base of products, expand its profitability, and help that industry, who has the expertise to handle these large amounts of materials.
And of course, for our region, New York State in particular, the paper and pulp industry is a very important component of our economy, correct?
Yes, it is. I believe the pulp and paper industry is probably one of the largest landowners in New York State. Plus, there are quite a number of mills in New York State that produce pulp and paper, and they are an employer, a major employer in the state.
Dr. Scott, thank you very much.
Thank you, Don.
Appreciate it. That's Dr. Gary Scott. We thank him for being our guest today, and also Dr. Thomas Amadan. And that's our show for today. Improve Your World will be back soon. Hope you'll join us. I'm your host, Don Torrance. We'll see you again soon.